Okay, here's our, let's see, another formula on compounding this continuously, like not just a set amount of times, but kind of always earning interest on your interest. Okay, so this is continuous compounding. Okay, so it's kind of saying in this part of our formula right here, this b, and as our n gets bigger and bigger and bigger, and it just keeps growing and growing, what's happening to that whole part of the expression. So that's what they're showing you right here. They're really showing you what happens. They're having you plug down here, and you don't have to do this. I'm just going to explain it to you. Down here, that 1 plus 1 over x to the x, that's that b part, okay? And they're having you just with a rate of 1, just to show you what's happening as the number of times, n, or in this case, x, what happens as it just keeps growing and growing. So they're having you look at a table to show you that as that keeps growing and growing and growing, it approaches some number. This whole expression actually just approaches a number. You may have seen this, you may not have seen this number before. Okay, so I'm going to jump down to actually the box where they're summarizing. Okay, so as this part right here, as x gets bigger and bigger and bigger, this whole part of our expression approaches what we call this e. Okay, and e is used to represent that whole piece as x gets very, very large. So you want to think of e really just like you would think of the number pi. It is irrational, just like pi is. Okay, it's really just a number. So when I see it into a formula, I can just use e on my calculator. There's an e right on your calculator. I don't have my calculator in front of me, but if you look at it, it's above a certain key. So you have to do second to get to it. But it is just a value just like pi. Okay, so if you do go on your calculator and you find that e and figure out what it is, e is approximately, if you look, even they're showing us at the end of the table over there, okay, e is approximately 2.7182. That's just the first 4 decimal places of it. It does go on and on forever, just like pi does. It's an irrational number. So you're going to see this actual value in a formula if the interest is compounded continuously. Okay, so really we're just using this 2.7182. It's actually easier to just use e on the calculator because then it's not rounded. Just like if you had pi in something, it's easier to use your pi key rather than 3.14 because it's not quite as exact. So let's just look at examples. I don't want you to get bogged down on where it comes from because that's kind of a little bit beyond this course. But let's just accept that as that expression gets close, as x gets bigger, this gets close to about 2.7182. Okay. Here we go. I thought I was missing a slide there for a second. So here's kind of the summary of what we were just talking about. So if it's compounded continuously, if our interest is compounded continuously, then we can use this formula right here. So if you notice, this is just kind of replacing our b. So we have e to the rt. Okay, so r is our rate, p is our principal, t is still number of times, and e is that base. Okay, so let's say we have $100 at a rate of 4% compounded continuously. So this means it's not a set amount of times. Okay, how much money will you have after 5 years? So if you follow the example right here, we have our p. Remember, e is just its number itself. We have our r right there, 0.04, and we have for 5 years. And we end up figuring out that 122.14, $122.14. So let's calculate the balance of your $10,000. If we got our interest compounded continuously, let's go back to our original problem of investing that money. So the amount we're going to have at the end would be $10,000. It's compounded continuously, so we're going to use e to the 0.065 times 10. So we do that part first. We do 0.065 times 10 first. Then we raise e to that power. And we end up figuring out that we have $19,155.41 at the end of 10 years. Okay, so it's actually 6.5% is a really big rate. But after 10 years, our money has almost doubled. Okay. Okay, so you can see that this b, our growth factor in this, is that whole piece, e to the 0.065. So if we want to determine that growth factor, well, we were just going to figure that out. What is e to the 0.065? And if you calculate that out, you end up getting a 1.06716. Okay, so what's the effective yield then? Okay, so this right here is my growth factor. What's my growth rate? Well, it's 1.06716 minus 1. So it's 0.06716, or in other words, 6.716. So that's how much interest we're yielding if it's compounded continuously. Okay, so historically, investments in the stock market have yielded an average rate of 11.7 per year. Suppose you invest $10,000 in that account. Okay, let's figure out our balance after 35 years. So our amount that we're going to make would be 10,000 times e to the 0.117 times 35. Okay, that's all in my exponent. Let's see. Actually, we're just doing, let me just erase that one little piece, that 7. We're just going to do 11%, it says in there, not 11.7%. Okay, so I do that exponent first. I figure out this first, then do e to that power, times it by 10,000. And this can kind of blow you away at how much it is. So $469,930.63 after 35 years. And that is not investing any more money. Okay, that's strictly your main principle, not putting any more in, but leaving it all in and just having it earn interest. If we did this for 40, we end up with, I'll let you do the actual calculation, but we end up with $814,508.69 from an original investment of $10,000. So that's pretty amazing. So at the beginning of this activity, your grandfather had claimed that you could grow to more than $500,000 by retirement for 40 years. Is it feasible? It certainly is if you're not touching any of that money, and that would also have to assume that the stock market is doing well. 11% annual interest rate would be that it's doing well, but over time that could certainly happen. So in your summary down here, you've got kind of 3 different formulas, okay, and it all depends, whatever one I'm using depends on how it's compounding. Okay, so if it's just compounding interest and we know how many times a year it is, well then we're going to use that regular formula. You'll know because you'll have an n value in the problem. Compounding continuously is where I use that e. Okay, and you'll notice that these formulas become the same as n gets really, really large. Okay, so it's not ever going to hurt to use either one really, because they are the same formula. One is this one right here is designed as n is compounding continuously, so over and over and over. Okay, so do some practice problems for this before you start your homework. There's some good ones right here on your next activity, the exercises for activity 3.5.